time. So as they bounce that carrier, they can't split it and bounce in two places at once. It's either over here or over there. All right. Let's move to this. In digital, we now have digital everywhere, don't we? And we install what's called digital cable, and modems are digital as well. So in digital, we have something called 64 QAM and 256 QAM. You guys ever heard of that?
Yes, I don't know what it is.
Okay, well, you're getting ready to. You're getting to learn what QAM is, okay?
Yeah.
So now we know, here's how analog cable channels work. Here's what a digital channel looks like. Then I'm going to explain to you how it works. Let's imagine that we could draw a box on top of here, and it's just an imaginary box. And this imaginary box goes from, say, 100 megahertz to this line could be 110, and this line could be 120. And let's say from here it was at -10. The middle line is 0, and the top line is 10. Okay, now if we're able to bounce our carrier left and right, that's pretty cool. We can also bounce it up and down. What if we could do both those two things at the same time? What if we could bounce it up and down and left and right at the same time? And let's say that our receiver at the other end, say the modem or the box, could decipher that. Okay? So let's say if we bounced it here, and the in between 0 and -10 would be -5, and here between 1 and 110 would be 105. So if we bounced our carrier at -5 dB at 105 megahertz, we should be able to do that. Boom, bounce the carrier there real quick. We would then fall into this box. And as long as our device on the other end can see that and decipher it and say, hey, that was -5 and 105 megahertz, then it knows that we're going to name these boxes. And so this box here, we're going to call it, we'll start at the top. We'll call this one 0, 0. We'll call this one 0, 1. We'll call this one 1, 0. We'll call this one 1, 1. Okay? So now that we've named these boxes, we just gave them names, and we're able to control this and create this carrier and bounce it right there, and the guy on the other end can see where we bounced it, and he knows that -5 and 105 equals 1, 0. Well, now for any moment in time, or for any instant, how many pieces of information are we sending? 2. A 1 and a 0. Okay? A 1 and a 0. All right. In this scenario, in just analog, we're able to send a 0 or a 1 or the other. One piece of information. Here, we're able to send 2 pieces of information for any instance or moments in time, right? Well, those pieces of information are called bits, 1s and 0s. Okay. This is called QPSK. You guys ever heard of that? It's how modems used to talk back. They don't anymore. Now they use what's called 16 QAM. You guys ever heard of that? Well, there's 16 QAM. There's QPSK. So there's FSK, QPSK, 16 QAM, 64 QAM, 256, 1028. Actually goes up a little bit more. You guys probably know 64 and 256, right? The most. But this is called QPSK. It stands for Quadrature Phase Shift Key, and really it just means for QAM. QAM stands for Quadrature Amplitude Modulation. That kind of makes sense, doesn't it? These are quadrants. I remember that when I was a kid. I remember quadrants, X and Y axis, not much. I don't remember a lot of it, but I remember a little bit, right? Those are quadrants. So it's Quadrature Amplitude Modulation, QAM. All right. If we divide this box up, each one of these boxes up another time, how many boxes do you think we have there?
16.
16. What do you think that's called?
16 QAM.
16 QAM. You guys are sharp as knives. I'm telling you what. 16 QAM. Okay. There we go. Now that I got more boxes, I can come up with more names, can't I? Because I can only find 2 names here. I can only find 4 names, 4 possible names if I only use 1, 1, and 1, 0. But now that I got 16, if I use 3, I can call this one 0, 0, 0. This one could be 0, 0, 1. This could be 0, 1, 0. This could be 1, 0, 0. You get the point, right? So now how many bits of information am I sending whenever in any second? 3. 3. Exactly right. 3 bits. Now everything I say here is not exactly right. I'm skipping some things and I'm saying some things wrong. I'm not going to tell you what I'm telling you wrong. This is just for example so you understand the concept, because the concept is what we're really getting at here. Alright, if I divided each one of these boxes, let me make me some room over here. If I divided each one of these boxes, again, and first I have my 4, and I divided each one again, and then I divide them each again. I'm not a very good drawer. How many boxes do you think we have? No? Take a guess. 64. Okay? 64. What do you think that's called? 64. That's it, man. You guys are so good. It's unbelievable. Now, this is something we've heard of, right? You guys have heard of this before, right? 64 quant? You heard of this, don't I? Okay. So now, let's say I'm able to make, we'll say, I'll use, for example, I'll use 4 bits. So we go 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. You get the idea. Name each box, right? And if you, now you're sending 4 bits of data for any moment in time or any instance. So, do you think it's a good thing or a bad thing to send more information at one time?
Depends.
Depends on what you're at. That's a good answer. Depends on what you're looking for. As far as trying to communicate stuff, it's good. You can send more information, but there is a problem with it, and that's why your answer is such a good one. Depends. It's because we'll digress here. Let's skip to one more thing, and we're going to come back to this. You guys have heard of MER and BER, right?
Nay.
Come on.
Serious.
Okay.
I'll lie to you.
All right. MER, BER. MER stands for modulation air ratio. Okay? BER. Does anybody know what BER stands for? Bit air rate. Exactly correct. Bit air rate. Well, if those are bits and they're aired and we're trying to bounce them in a certain box, what do you think an aired bit means?
Missing a digit.
It didn't hit the right box. Missing a digit is kind of, but it didn't hit the right box. It's gonna it's not gonna miss any digits. Wherever you hit it, it's going to send 3, but it might send the wrong one, right? So if it bounces over here, it sends the wrong one. Okay, so let's talk about that. So I'm just going to tell you what MER is. MER, as you bounce these dots in here, and when you bounce one there, and you bounce one there, and you bounce one there, and you start bouncing them around, you get something that looks like this. In cable TV, this is called the constellation. I think it's called the constellation because your meter, the background of the meter is black, and in cable TV we don't come up with very innovative terms for things. We just call them kind of what they are. And I think that looked like space to somebody, and those dots coming in look like stars, and they called it the constellation because it sounds so fancy, the constellation. But I bet you it's just because it looks like stars in the sky. At any rate, when these bits come in here, the transmitter at the cable head end, he was trying to send the bit to come in here. And he sent it out, and as long as it landed in here, then he communicated the right bits of information, the right 2 bits, in this case 0, 1. He sent the right information. He wants to try to be dead center, because as he goes down the line and the wind blows, things can screw things up, and in the end he might not be exactly where he was, right? You can do all the math you want, but when you go to the house with your meter, you might not have exactly what you thought you had. Okay, the splitter, you did all the add and everything, but it doesn't come out exactly right. But it is what it is. So in the end, he tries to aim for the dead center, but he often has some issue there, and it never goes quite to the center. How tight it is towards the center is called MER, modulation air ratio. The tighter you are, the better. You want the number to be high. I have no idea why you guys are laughing. All right. So as with everything else in the world, the tighter the better. The tighter that is, the better it is, and you'll come up with some equivalent numbers that let you know how tight that is and how good that is. And those numbers are, you can apply those to other things, but they are, usually you'll have